Welcome to Puzzles to Exercise the Mind Lesson 5. We're going to talk about the pigeonhole principle and various versions of that in this lesson. And then towards the end, there's a little bit on graph theory, but even there it's related to the pigeonhole principle. We have a couple of easy puzzles here, and they're related to the pigeonhole principle, which I'll explain on the next slide. But let's look at the first one. You have 10 black socks and 10 white socks in a drawer. Which the minimum number of blind draws from the drawer to ensure that you get 2 socks of the same color. So maybe you're kind of sleepy and you're turned one way and you're looking one way and you're kind of reaching into your drawer that has socks and you're picking out one after another, and you want to get 2 of the same color. So you go in there and you get a white sock, and then you get a black sock. That's pretty much the worst case, that you don't get a pair in the first 2 tries. And then whatever you pick the third time is going to either be white or black. So the minimum number of selections that ensures that you're going to get 2 of the same color is 3. And that's a version of the pigeonhole principle, although it may not be obvious why it's related to the pigeonhole principle. You'll see as we go through some more of the puzzles here. Then the second one's a little bit harder. You have 12 people, they go into an elevator, and let's say they're on the bottom floor, ground floor, and then above them is floor 1, 2, 3, 4, and 5. And is it true that 3 people get off on at least one floor? So we assume they all get off by the time you hit the 5th floor. So right, so everybody gets in on the ground floor, door shuts. What's the worst case scenario in terms of not having 3 people get off? Well, you have 12 people, so if you have one person get off, if you had 2 people get off on each floor of the 5 floors, that would be 10, and you still have 2 people left. So they would have to get off on one of those 5 floors. So it is true that at least 3 people have to get off on one of the floors, assuming that, again, that they all get off by the time the elevator hits the top floor. Okay, so that's this is a variation on the pigeonhole principle, and we'll talk about both of these. Actually, there's 3 variations. We'll talk about all 3 of them as we go through this lesson. On this slide, we have the base version of the pigeonhole principle, and this is the one you may have seen before. I have kind of a theoretical definition here, a little bit technical, I guess is maybe the right word, and then I'll give you an example here on the bottom. But let's look at the technical definition first. So you have 2 sets. One we'll call set 1 and set 2. So the first set has n items. They're identical items. There's no difference between them, and which you want to associate each item in set 1 with exactly one item in set 2, which has m items, and where n is greater than m. And if that's the case, if m is greater than n, then at least one of the items in set 2 must have more than one item from set 1 associated with it. So let's look at an example to maybe make this a little bit more concrete. So let's say set 1 has 4 elements, and they're balls, green balls, let's say. And then set 2 it has 3 items, and they're containers. So we want to associate each ball with exactly one container, which is done by just putting the ball in the container. So since our n is greater than m, the number of items in our number of containers, then clearly you're forced to have at least 2 balls in one of these 3 containers. Right? You could put one here, one here, one here, and then the 4th one you have no choice but to create a container that has 2 balls in it. So that's all we're saying here. The original idea came from actual pigeonholes, where you can think of these as being 4 pigeons, and then you have 4 slots to put them in, and you have no choice. If you want to put each pigeon in a slot, you have no choice but to put 2 pigeons in one of the pigeonholes. So that's kind of the general idea. There's 2 more versions of this which we'll talk about, but first we'll do a few more examples, then we'll get to the generalizations of this principle. This puzzle may not seem to be a pigeonhole puzzle from first reading, but in fact it is. So let's have a look at it. Suppose that you have a collection of many marbles in a box, and the marbles are 4 different colors: red, green, blue, and black. What is the least number of marbles that you need to retrieve from the box to be sure of getting 2 marbles of the same color? So the reason I said many marbles here, I just wanted to emphasize that you're not going to run out of red, green, or blue or black marbles when you're doing the selection from the box. But the question is, what is the least number of marbles to retrieve from the box to be sure of getting at least 2 marbles of the same color? So it looks a little bit like the sock drawing puzzle that we talked about before, except now we have 4 different colors instead of just 2. So you may want to think about that a little bit before we talk about the solution, which I'll mention on the next slide. As I noted on the last slide, the puzzle doesn't look like a pigeonhole puzzle at first viewing, but if you think about it, we can let the 4 colors be the pigeonholes. So set number 2 in our definition, and that would give us m equals 4. So we have 4 slots, so to speak, to fill. And we are being asked to find the smallest number n such that we're sure to draw 2 marbles of the same color. So one can view set number 1 as the draws, and the smallest value n to ensure the desired result is 5. Right? We need to have more than the 4 colors. Another way to look at it is the worst case analysis. What is the worst case in terms of not getting the 2 marbles? So you would, sort of like with the socks, except now we have 4 colors, you would pick a red, then a blue, then a green, then a black, and you'd have 4 marbles with no matches. And then when you go in there for the 5th marble, you have no choice. I mean, no matter what color you pick, you're going to get a second of one of these 4 colors, and that would, so that the minimum is 5 draws from the container holding the marbles to get 2 of the same color. Now that we've seen a few of the pigeonhole puzzles, this one should be rather easy. We have a hotel, small hotel that has 10 rooms and a 10-slot mailbox, 1 slot for each room. And let's say that the slots are all empty when we start this puzzle. The question is, what is the least number of new letter arrivals before at least one of the mailbox slots must have 2 letters? So if you want to try this, pause the video, and I'll come back and give you the answer in a minute. Okay, so we can do a worst case analysis to solve this. We envision having 1 letter come in for each of the rooms, so that populates each slot with 1 letter. And then the 11th letter would necessarily need to go into a slot that already has a letter. So, and that would give us the 2 letters in 1 slot. So the answer is 11. That's the least number of new letter arrivals that forces or guarantees that you're going to have at least 2 letters in one of the mail slots. Okay, on the next slide, we're going to talk about the first generalization of the pigeonhole principle. On this slide, we have what's the first generalization of the pigeonhole principle. We've been using that already a few times, but I'm going to state it formally here. So if each item in a set of k times n plus 1 items call it set 1, is to be associated with one item in another set called set 2 that has m items, then at least one item in set 2 must have k plus 1 items associated with it from set 1. Okay, so that's quite a mouthful. Let's see if we can make it a little more concrete with an example, which I have here in the second paragraph. So let set 1 consist of 3 times 10 plus 1, 31 identical balls, marbles, whatever objects you like, but they're all the same. And so our k is 3 and our m is 10 in the theorem here. And let's set 2 be 10 containers. And we want to associate one ball with a container. So this generalized pigeonhole principle tells us that at least one of the containers has k plus 1 or 4 balls. Let's maybe take a step back and do a worst case analysis. So we want to, if we try to avoid having 4 balls in one of the containers, one of the 10 containers, how would we, how close could we get to doing that? Well, we could put 3 balls in each of the 10 containers, and then we would have had 30 balls distributed. And now we're forced with that 31st ball to put it in one of the containers, and that would give us 4 balls in one of the containers. So we can always revert back to the worst case analysis. Try to not do what's being sort of guaranteed by the principle, and you end up seeing that you have to have that one additional ball in at least one of the containers. Now, remember that we're talking worst case. Things could happen even sooner. We could have 5 balls in one of the containers if we're just throwing them in there randomly, and that would already satisfy the condition of this generalized principle. Okay, so it's a little bit confusing. Sometimes the general statement can throw you off, and it's easier to maybe look at some examples and then say, okay, now I see it. They all fit this general pattern here in this generalization number 1. Here's a picture of the example we talked about on the previous slide. We have m equals 10 and k equals 3. And so k times m plus 1 is 31. So we have 31 balls to associate and put in to 10 containers. And doing the worst case analysis, as I described before, trying to avoid having 4 balls in one container, it's not possible. And you can see that here. The best you can do is put 3 balls in each of the 10 containers. And then the 31st ball, you have no choice but to fulfill the generalization number 1 of the pigeonhole principle, in this case having 4 balls in one container. So here's a visual picture. Keep in mind the containers are identical and the balls are also identical. So that's the condition of the generalization number 1. Okay, so again, if you get stuck or with some of these example generalizations of the pigeonhole principle, the easiest thing is to try to do a worst case analysis and try to demonstrate that you can't fulfill what's being guaranteed in the theorem, and then that kind of reveals that the theorem is in fact true, because you can see, like we did here, when you have that 31st ball, you have no choice but to fulfill what's being claimed in the generalization number 1 of the pigeonhole principle. Okay, this problem is a variation on the previous problem. We consider a box with 4 types of marbles and determine the least number of draws that are needed to ensure that at least 5 marbles to get at least 5 marbles of the same type. So you may want to pause here. I'll give you the solution on the next slide. Let's start with the worst case analysis solution to the problem stated on the previous slide. I think that's going to be easier to see. And then I'll show how it maps to the pigeonhole principle generalization number 1, which is not as easy to visualize. But let's start with the worst case analysis. So let's model this as a large container that has all these 4 types of marbles, and we're going to draw them out randomly, so we're not looking at what's being selected, and we're going to put them into 4 stacks or 4 containers. So we'll have a container for the black and another one for the white marbles, and so on. And doing the worst case analysis, we want to say what's the largest number of marbles we can draw out of here before we're forced to draw a 5th marble of a particular type. So the worst case is that we get, and I know this is improbable, but the worst case is we could get 4 black, 4 white, 4 gray, and 4 black with a white center, and we would not have 5 of a particular type. So on that 17th draw, then we're forced to have at least 5 of one type of marble. So I've shown here where it's a gray, but it could have been any of these colors. So the answer to the problem is that 17. That's the least number of draws from this collection of 4 types of marbles that guarantees you're going to have 5 of one particular type. So I think that's kind of easy to see. What's harder to see, as I said, is mapping this with the pigeonhole principle generalization number 1. I copied the principle up here, and let's see how we can map what we have down here to what's in this principle. So and the first problem we run into are the sets 1 and 2. If you recall, I said all the elements in set 1 were the same, and all the containers in set 2 were the same. So that we kind of have a difference already here, but it still works. So we can have M would basically represent the colors of the marbles, or the types of marbles. So M would be 4. And then we want to have at least one item in set 2, one of the containers in set 2, which are of these 4 different colors, would have K plus 1 items. So our K plus 1 is 5. So we can work backwards and say, well, that means K is 4. And so what we're asking is, what does this expression need to equal to in order to force us to have 5 here? And so we have K equals 4, M equals 4, and we add 1 to that and we get 17. So working backwards from the input, we have M being 4 and K plus 1 being 5, we could figure out what this number needs to be, and it's 17. So again, probably not the easiest way to solve the problem, but I wanted to make the point, I guess 2 points here. One, this fits into this problem fits into the pigeonhole principle, and 2, we can kind of extend the pigeonhole principle where we have multiple types of items in set 1, and we have and they're assigned to a particular type of container in our set 2. So there's more than one type of container in set 2. And if you think about this, we could have made an easier version of this problem where we had all the marbles of the same color, same type, and we had 4 containers, and then we could ask, what's the least number of marbles that we pull out of this larger container and putting them into these smaller containers in set 2, such that you have at least 5 in one of the containers, and that would be the same answer. The only difference from that problem and the original problem is that we have 4 types of marbles, but we're forced to put those into a particular type of container, one of 4 types of containers. So the 2 problems are equivalent in terms of the solution. Okay, I hope I didn't confuse you too much. As I say, what seems like a simple principle, this pigeonhole principle, can kind of get a bit hairy when you're just kind of have the problem thrown at randomly at you, and you're not even told that the pigeonhole principle is the way to solve it. Okay, so we'll do a few more of these. Hopefully, things will become clearer as we look at more examples. We have one more generalization of the pigeonhole principle, which we'll call generalization number 2. We have two sets, set 1 and set 2 as before. Set 1 has a sub 1 plus a sub 2 plus dot 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 plus a sub n minus n plus 1 elements, which we can distribute the minus n and just take minus 1 n times and subtract it from each one of the a terms here, and then we still have the plus 1. So that's the number of items in set 1, and each item in set 1 is to be associated with one element in set 2, which we'll represent as containers. And set 2 has n elements. Notice n here is the same as the number of these a sub 1, 2, all the way up to a sub n. So that's a key part of the theorem. Then if we do this association, then there exists a number j, so in other words, a container j in our set 2, such that an item, that container in particular, has a sub j or more associations with items in set 1. So kind of complicated. Let's see if we can think about it in another way. So let's say we have the n containers, as I've alluded to. So that's our 1, 2, 3, 4, all the way up to n. So that's our set 2. And assume container I, where I goes from 1 to n, has a sub I minus 1 items. So we have a sub 1 minus 1 in container 1, container 2. We're basically doing a worst case analysis here. So we distribute the items, let's say they're balls or marbles, we distributed that many items into these n containers. So what happens, so far, I guess we should say, none of these containers has the a sub j number. So in other words, a sub, this container number 3 does not have a sub 3 number of balls in it. Same for 2, same for 1. So we basically went as far as we could go without having any container having the associated number of balls for the a sub j. And if we add one more ball, which would give us this number here, we add one more ball, then we're forced to have one of these containers with a sub j balls in it. So let's just say it's we put it in this one here, container 3. So we take the one more ball in this to make this satisfy this number here, a number in set 1. We put it into this container. Then this container would have a sub 3 balls in it, and that would satisfy what's being claimed in this theorem. So it's a little bit abstruse, I guess. We'll look at a couple of examples where we use this, and when in doubt, just try to do a use case, a worst case analysis, and that's usually helpful in understanding these different pigeonhole principles. Okay, so we're going to do an example next and see if that helps make this a little bit clearer. We have an example here of our pigeonhole principle generalization number 2 that we just talked about. Assume someone wants their pocket change to have at least 4 $half, or at least 8 quarters, or at least 20 dimes, or at least 40 nickels. What is the least number of coins that this person needs to select from a jar of coins, assuming there are more than 100 of each type of coins in the jar? So in other words, you're not going to run out of coins, and again, this is a blind selection, and you want to get at least $2, as I restated it down here. What is the least number of coins that needs to be blindly selected from a jar of half dollars, quarters, dimes, and nickels to ensure $2 in change of a particular coinage. So in other words, half dollars, quarters, dimes, and nickels. I know that's a bit of an odd thing. You know, why wouldn't you be happy with two half dollars and four quarters? But that's an example that kind of fits with our pigeonhole principle. So let's see if we can figure out how to use the principle to solve this and figure out what's the least number of line selections from the jar in order to get our goal here. Okay, so if you want to give it a try, pause the video here. Otherwise, I'll give you the answer on the next slide. We can solve the problem concerning the coins from the last slide using the generalization of the pigeonhole principle, generalization number 2. So we'll let n equal 4, since we have 4 types of coins. And then what we need to attain the $2 of coins for each type of coin I've embodied here. So A1 would be 4, so you need 4 half dollars to get to $2. Or you need, we'll let A2 equal 8, so you need 8 quarters, or A3 represents the dimes, so you need 20 dimes to get to $2, or A4 equals 40, and that's the 40 nickels. So our A1, A sub 1, A sub 2, up to A sub 4 minus n plus 1 is 4 plus 8 plus 20 plus 40 minus 4 plus 1, so 69. Our answer is 69. This is the minimum number of selections, blind selections, random selections from the coin jar to ensure at least $2 in change of particular coinage. So you can look at it again using the worst case analysis. So one could draw 3 half dollars and not have $2 yet, 7 quarters and just be short of $2, 19 dimes, 39 nickels, and in each case you'd be 1 short of what you need to get to your $2. And if you add up these numbers here, the 3, 7, 19, 39, you get 68. And so the next coin you pull out is going to, whatever it is, half dollar, quarter, dime, or nickel, you're going to have at least one set of coins of the same type to give you $2. So that, again, this, if you have trouble with the statement of these pigeonhole principles in general, I would look at the worst case analysis, which kind of embodies what we've done up here, but it's maybe a little bit easier to see mentally. Okay, so I have this in my book. One of my books is called Learning Math Through Puzzles. I self-published the book on Amazon, and I've made the electronic versions of all my books free. You just go to my website here, and then there'll be a list of books, and look for this particular one here, and then click on the electronic version, and you get a PDF file. And then you can you'll find there's a whole set of problems in there related to the pigeonhole principle. So actually, a lot of what I've shown you on excuse me, on the last couple of slides, I've taken out of my book. It was a little bit of changes and some, of course, some wording behind it. So there's other puzzles in there that may be of interest. So you may want to take a look at that. And if you like it, send me an email. I have my email address at the very beginning of the book, and I'm always happy to hear from people who like the stuff that I write. Okay, so let's go on. We have a few more puzzles in this lesson. So prove that for any set A of 100 natural numbers, so that's whole numbers, and they don't need to be in order. You could have, or should I say, they don't need to be consecutive numbers. So it could be 25, 36, 100, 5,000, 10 million, whatever. There's just has to be 100 of them. Then either one of the numbers is divisible by 100 exactly. So in other words, you divide by 100 and you get a remainder of 0. Or the sum of some subset of the numbers in this set A is divisible by 100. So I'll give you a clue. We can solve this using the generalization number 2 of the pigeonhole principle. I'm going to have some intermediate material before I get to the solution of this. The solution will be at the end of the slide set. So if you want to try this, go ahead. It's an interesting problem that you can actually prove this, because it's not obvious why that should be true just looking at the statement of the problem, but in fact it is. Well, the next slide I'm going to give you a pigeonhole problem related to graphs, but I need to first explain what a graph is. It's pretty simple, and you may already know what it is, so this could be just a refresher. So a graph is a collection of vertices, these little black dots here, and edges, which connect between the vertices. So in this graph here, we have 1, 2, 3, 4, 5. We have 6 vertices. We have 1, 2, 3, 4, 5 edges. And I put a label on some of the vertices here, A, B, and C. C is an isolated vertex. It's not connected to any of the other ones here. And then we also have something called the degree of a vertex, and that's how many lines are coming out of the vertex. So you have how many edges, I should say. So vertex A has degree 3. You can see that here. It's 1, 2, 3 edges that originate out of A or terminate on A, however you want to word that. Vertex B has degree 2, since it has 2 edges coming out of it. And C, the isolated vertex, has degree 0. Okay, so that's it. It's pretty simple. There's a body of knowledge on something called graph theory. In fact, Euler, who we talked about in an earlier lesson, was one of the founders of this area of mathematics. You can find even a basic book on graph theory that has 400 or 500 pages. So there's a lot known about graphs, but we're only going to go so far. Here, we're just going to take a relatively simple example related to, as I mentioned, the pigeonhole principle, and that's on the next slide. Okay, so here's our problem that I promised. Show that in any simple graph, and I'll explain what that is in a second, show that in any simple graph containing a minimum of 2 vertices, so 2 of the little dots we had on the previous slide, there must exist at least 2 vertices with the same degree. And just to mention here, a simple graph has at most 1 edge between 2 vertices. So maybe I can just draw you a quick example. So let's say that's one vertex, and that's another vertex. Let's do blue. So that would be a simple graph. It just has 1 edge between the 2 vertices. And if I did that, that would be a multi-graph. We're not talking about that type of graph in this example. So in this case here, you have more than 1 edge between the 2 vertices, and that can happen. There's applications that require that, but for this problem here, we're only looking at simple graphs. So you may have assumed that from the way I defined the graph on the previous slide, but I just wanted to clarify here. At the top, I've copied the theorem that we want to prove. Let's assume we have n vertices where n is greater than or equal to 2. And that would mean that the possible degrees for the vertices is either 0, if we have an isolated one, all the way up to n minus 1, where we have a vertex that's connected to all the other n minus 1 vertices. Can't be connected to n because we're not allowing a vertex to be connected to itself. That's not a possibility in the way we've defined graphs. So we have 2 cases. In one case, there are no isolated vertices, and in that case, the possible degrees are 1, 2, all the way up to n minus 1. So there's n vertices, but only n minus 1 possible degrees that they could have. Then the other case is where there's at least one vertex of degree 0, but that would imply no other vertex could have degree n minus 1 because it wouldn't be able to connect to that vertex of degree 0. And so the possible vertices, degrees in this case, would be 0, 1 up to n minus 2. So in this case, we have n minus 1 possible degrees, but n vertices. And in this case, we also have n minus 1 possible degrees and only n vertices. And so from the pigeonhole principle, since we have n minus 1 possible degrees and n vertices, at least two of the vertices must have the same degree. So we've proven our theorem. On this slide, we return to a problem we stated a few slides back. I recopied it here. If you recall, we wanted to prove that for any set A of 100 whole numbers, natural numbers, either one of the numbers is divisible by 100 or the sum of the numbers in a subset of A is divisible by 100. So we'll prove it here. Let 100 whole numbers be these here. Since we don't know exactly what they are, we'll just use some variables here. So x sub 1, x sub 2, x sub 100. And again, they don't need to be in order. They could or consecutive. So this first one could be 2, this could be 7, the last one might be 5082. So any set of 100 whole numbers is the condition, and we want to show that either one of the numbers is divisible by 100 or the sum of some subset is divisible by 100. So we just consider all the possible subsets. That's known as the power set. I've just wrote a few down here. You can have all the subsets with just one single element, then all the possible was 2, and so forth. So think about those. And what we basically want to prove, I've kind of restated here in this second paragraph. Let's take the sum of each subset, divide them by 100. So in other words, we look at all these possibilities. It's actually 2 to the 100 sets, so a huge number of sets, but we divide those subsets, I should say. We divide each one by 100 and consider the remainders. If one of the remainders is 0, then the sum of that subset is divisible by 100 by definition of division, basically, and the original condition is satisfied. So that's what we want to show. If either one of the numbers is divisible by 100 or one of these sums, when you one of the subsets, when you add them all the members up and you divide by 100, you get a remainder of 0. So we want to show that. To that end, we first state if any of the numbers are divisible by 100 individually, then we're done. So let's say that's not the case. If none of the numbers are divisible by 100, let's consider the following sums. We'll call S1 just equal to x sub 1, and then S2 equal to x1 plus x sub 2, and then we just continue for all the members of the set. So we would have 100 of these partial sums where you start with the first one, then the first 2, then the first 3, and so on. All right, let's continue that on the next slide. Let's continue with our proof. We'll let r sub I be the remainder when our partial sum s, capital S sub I, is divided by 100. And in general, when you divide a number by 100, the possible remainders are between 0 and 99. If you had a remainder bigger than 99, say 101, that means you can divide by 100 one more time, and then your remainder is back under 99 or less. So for the problem at hand, our r sub I it must be between 0 and 99. So that gives us 100 possible remainders when we divide by 100 into one of these partial sums. Now keep in mind we have 100 numbers to start with, so there's 100 partial sums. One further notation, let little s sub I equal the set corresponding to the numbers in our partial sum here. we have two cases. Either one of the R sub i's is 0, which means that this set S sub I it fulfills the requirement of our theorem of basically a subset whose members, when added together, is divisible by 100. That's one case. Then the other case is that none of the partial sums has a remainder of 0 when divided by 100. So all these R sub i's are not equal to 0, which excludes one of the possible remainders here. So that leaves us with remainders from 1 to 99. So we have, in this case, 99 possible remainders, but 100 partial sums. So that means that two of the remainders must be equal to each other. So let's just say R sub I equals R sub j and I is less than j, which means that the remainder of S sub j, minus S sub I when divided by 100 must be 0. And if we look at what S sub j minus S sub I looks like, it's this here, because these are all in sequence, right? The members of these sets are in sequence, and we're saying j is bigger than I. So when you subtract capital S sub I from it, you're just eliminating all the terms x sub 1, x sub 2, all that up to x sub I. And then what's left is x sub I plus 1, x sub I sub 2, up to the x sub j. So this sum here, when divided by 100, has a remainder of 0. But then we have this set little s sub j minus little s sub I using set subtraction. So if we took all the elements in little s sub j, x sub 1, x sub 2, all the way up to x sub j, and subtracted the numbers, the members of little s sub I, which is x sub 1 all the way up to x sub I, then we get this set here, x sub 1, x sub I plus 1, x sub I sub 2, all the way up to x sub j. But then this set here is a subset of our set A, and we've just proven that it's divisible exactly by 100. So this set here fulfills the conditions of our requirement. I'll give you a little example in the next slide where I actually have some numbers in here. Maybe that'll help clarify this here, because this becomes a little bit dense in here, and sometimes you need to put down a specific example. So I'll do that on the next slide. So we have an example here that might make the theorem a little bit easier to understand, or should I say the proof of the theorem. I only took 5 numbers here, but I think it's enough to illustrate the point. So let's say our set A has the first 5 elements for 10, 20, 31, 49, 51. So the set of the first 3 elements is 10, 20, 31, and then the sum of those is 61, and the remainder, R sub 3, when you divide by 100, is 61. And then when we take the set little s sub 5, so all 5 of these first 5 numbers, we get the 61, and then 49, 51 is another 100. We get 161. But when you take the remainder divided by 100, you get 61 again. So this is what we were talking about in the theorem, when you have 2 remainders for 2 of these partial sums being the same. And so the difference, when you subtract these sums here, you get, in this case, 100, but it would be basically a multiple of 100. And so this difference is exactly divisible by 100. And then the set difference, when you take this set here and subtract these elements, so take these 3 off, you're left with this set here, 49, 51. And as you can see, this is not an accident. These 2 numbers, when added together and divided by 100, have to have a remainder of 0. So this is a simple example, but you can imagine where the set difference has even more numbers in it, but you still have the same conclusion that it's going to have to be divisible by 100. So I hope this helps a little bit. In general, when you get stuck with the theorem, especially when it involves the whole numbers and things you can do examples of, it's usually helpful to just write down an example, even though it doesn't prove the theorem. It helps you understand. In some cases, if you're working on a harder theorem, you might actually put some real numbers down and realize, oh, this is wrong. I must have had something wrong in the statement of the theorem, and it makes you go back and double check. So um, here we have it. So this is the last uh, problem in our lesson, but I plan to have several more. So keep listening, and if you like this, please click the like button and subscribe to my channel.